We have section 3.5. This is just a little more with bases of null space. Because I think that's the toughest one for people to deal with. And so let's look. Our original example, I need to go find that. Our original example I used, we had the matrix A was 1, -1, 3, 2, 3, -2, 3, 2, 1. And that row reduced to a matrix B. It was 1, 0, 0, 0, 1, 0. And then, let's see, what the heck was that? Oh, I think I have it here. It was, 7/5, -8/5, and 0, like that, when we did our row reduced echelon form. Okay, so the null space, we want to get it from here, and here's a technique to generate that row space. Okay, look here, down the diagonal, you see 1, 1, and then a 0. Well, make everything square, and make it square in this fashion. So right now, it's not exactly, the non-zero stuff is not square. It's 2 by 3. So we need to add another row, and I know which row I want because I have this starting, and what I want to do is sort of complete it with making the identity using that row. Okay, and then now, if I add that row, though, I'm going to use a -1 instead of a 1. And then here we've got our 7/5 and -8/5. And what I've done here is set this up so that now all I have to do is take the negative of that column, and technically I don't even have to do that, but usually we would. And what we would say is our null space of A is equal to any constant t times then the negative of that column. So -7/5, 8/5, and 1. And if you were to check back at the other video, that is what we got. And again, where is that coming from? Why does that make sense? Well, this first row says x1 plus 7/5 x3 is equal to 0. And then the second row says x2 minus 8/5 x3 is equal to 0. And so those two we could rewrite as, an x1, x2 is equal to x3, whatever it is, times 7/5 and -8/5. Okay, oops, sorry, -7/5 and plus 8/5. Okay, just like what we have up here. So, right, I just move these over to the other side, and that's what we have. I factor out the x3, and it says, this x1, that x2 needs to, they're both some constant, whatever I choose x3 to be, times -7/5 and plus 8/5. Okay? Now, though, well, x3 is part of this. Oh, well, I can finish that out by saying, tack on an x3 at the bottom, and Oh, well, tack on a 1. Well, there you go. Okay, so x3 times that. Now, though, in terms of, notice, in terms of this vector, how did I sort of see that coming, or what would I have done back here is these are all, it's the positive 7/5, that's negative 7/5. I got a negative 8/5, I got a positive 8/5. And so here, if I have a positive 1, I need a negative 1 right there. And so I put that negative 1 there. And that's what this technique is doing. It's just kind of a, once you do it a few times, it becomes sort of a non-thinking technique. It's just a way to get the calculation done and get it done correctly. And so that's what we're doing, and kind of that's the method is I try to square everything up and create an identity matrix. And so the second example I did with Sage was I took that original 3x3 and I tossed some more to it. So I had 1, 2, 3. Whoops, not sure what just happened, but I was looking at my computer with the Sage output here. Negative 1, 3, and 2. 3, negative 2, 1. 5, negative 3, and 4. And 0, 1, and 4. Okay, that was A. And then B, the row reduced echelon form, is 1, 0, 0, 0, 1, 0, 7/5, negative 8/5, and 0. That's no surprise because that's what I started with before. Then 0, 0, 1, and then 31 over 5, and negative 63 over 10, and negative 5/2. Okay, so as I look at this, my null space, the basis for that is going to come from these two. But the way I'm going to generate that is that same idea. Is notice, here I'm heading down nicely for the identity, but then all of a sudden it jumps over 1. I need to insert a row right here that goes 0, 0, 1, 0, 0 in order to kind of get all these 1s to line up down the diagonal. And again, I'm going to actually do a negative 1 because of, all this mess of moving things to the other side of the equal sign. And then I'll still be short a row because that'll make 4 rows but 5 columns. So then to square it up, well, that 1 is here. I just need to add then another row, 0, 0, 0, 0, 1, but again, make it negative and put that at the bottom. And so my new matrix, I don't know, B hat, is 1, 0, 7/5, 0, 31/5, 0, 1, negative 8/5, 0, negative 63 over 10. Now I introduce that row, 0, 0, negative 1, 0, 0, and you see how I'm going down the diagonal now very nicely. Add the 4th row because that had the 1 in the 4th column, 0, 0, 0, 1, and minus 5/2. And then finally I add that last row, 0, 0, 0, negative 1, and you see now I've made a 5x5 nice square matrix. And what I can do to get my basis from this, I just take the negative of that column and the negative of that column, and so my null space of A is generated by what? The negatives of those, negative 7/5, 8/5, 1, 0, 0, And do that. There we go. And 31, oh, negative 31 over 5, positive 63 over 10, 0, 5 halves, and 1. And there we go. There I have my basis vectors for my null space of A. And so, using this technique, not bad at all. And again, where did this come from? Well, let's just, look at that equation, right? There's x1, x3, x5. And so this said x1 plus 7/5 x3, and then plus 31/5 x5 is equal to 0. And then the next row said x2 minus 8/5 x3 minus 63/10 x5 is equal to 0. And then the third row of the original reduced row echelon form said x4, was that a minus? I think, yeah, minus 5 halves. So minus 5 halves x5 is equal to 0. And so then if we were to write, x1, x2, now I'm going to skip a space and go x4 as a big vector, that's equal to, and you see I would have negative 7/5 and a positive 8/5 and a 0 down here to go with the x4, all times x3, and then plus an x5 times negative 31 over 5, positive 63 over 10, and then skip a space and go down here to the x4 and it'd be 5 halves here. So there's x3 and x5, but you see I could toss x3 in here and put a 1 there and a 0 there. Okay, so x3 is fine because we don't want x5 messing with x3. x3 is arbitrary. It gets to choose its own fate. And then I can put an x5 at the bottom and put a 0 there and a 1 there. So that is where that extra 1 and 0 are coming from. Okay, that one, and that 0, and then that 0 and that 1. Again, making them negative because technically when we're working with this matrix, we're on the left side of the equation, and we want to move everything to the right side of the equation to make the 1's positive. So we'll make those negative 1's to start with. Okay, but it is, that we will just add some rows with the proper 1's and 0's in them to create that diagonal and make a square matrix out of our non-square reduced row echelon form. Okay, so hopefully that helps with the null space. I do find that seems to be the hardest thing for people to do is come up with the basis vectors for the null space. But there we go. So we've got a few different videos that kind of look at this in different ways to try to get at it. But there is more about null space and basis vectors.